the number e. The number e is an irrational number, and you guys should have seen it before. You should have seen it in 105, or whatever other math class that you took before this. And here's a decimal approximation. I usually do 2.718. So it's like pi. It's a very important number in finances because of how it actually was found out. So if we compute the continuously compounded interest of an investment, so if we do the interest of an investment, we usually do 1 plus the rate times time times the principal, which is almost what we just did in that one example. So this actually gives me exactly, so this is if we're compounded annually. And we'll go into this a little bit more at the end of this chapter. But if we go 1 plus r over k to the kt, where k is the number of compounds per year, then let's say I compound twice a year, so semi-annually 1 plus r over 2 to the 2t, where t is the number of years. Or if I do quarterly, it's 4. Or if I do monthly, it's 12. I can do daily, I can do weekly, but the more that I do, the closer I get to this crazy thing that looks like this. So I get this crazy thing that looks like this. This is compounded continuously. It looks like this. And we're going to use the calculator. If I use the calculator and I showed you various, so if n is only 1, that's just 2. 1 plus 1, then to the 1 power, it's 2. If I put in 2, it's 2.25. Put in 4, it's 2.44. And you can see what happens. If I do 365, it's 2.715. Look, if I put in 1,000, 100,000, or 1,000,000, you can see what's happening. We're getting closer and closer and closer to a certain number. And if this is the graph of it, I'm getting closer and closer and closer to this number, this asymptote, if you will, called E. So if I say that I'm continuous, if I'm doing this if I'm compounding continuously, that's what I'm trying to say. If I'm compounding continuously, then what I'm really doing is just multiplying it by E. So I'm taking my principal times E to the rate times time. And that's it. So that's where I get that number. So as n gets bigger and bigger, this becomes this gets closer and closer. This whole thing gets closer and closer to E. So if we continuously compound interest, the number of compoundings per year gets infinitely large. So here's my formula for exponential growth. If a quantity P increases or decreases at an annual rate R compounding continuously, then the amount A after T years is given by this. It's A equals PERT, and you've probably seen this before. If time is measured in years and R is called the annual growth rate, if R is negative, then it's not really growth, it's decay. Because if R is negative, then remember, instead of going this way, we're going this way. Okay, so let's do an example. Continuously compounded interest. If $20,000 accumulates interest at an annual rate of 10% compounded continuously, find the balance in the account after 30 years. So our principal, $20,000. Our rate is 0.1, because 10% is 0.1. T equals 30. We have A equals P e to the RT. So that's 20,000 e to the 0.1 times 30. Now let me show you how to put that in your calculator. Turn it on first. That's always nice. Okay. Good. All right. So we know we have 20,000. Your E is right here. It is the second natural log. So e to the, some of you have a thing that comes and say exp with the parentheses. That's the same thing. 0.1 times 30. Enter. So that's a lot of money. Good luck finding something like that, but you know. So you would end up with 401,710. Boy, I cannot talk today. And 74 cents is what you would have in that account at the end of 30 years. That's a long time to leave something in an account. So let's do another application problem. Now, a lot of times we use radioactive material, and we're not really going to do that. We're actually going to do coffee. So, as the material emits radiation, the amount of radioactive material that is present decays exponentially according to this formula. So, the amount A of a radioactive material present at given time t, A naught is the original amount. That actually stands for A naught, which is the initial amount. And K is a negative number. So if this is negative, remember this is going to now look like this and be a decay. And we're going to do some, I don't have any examples. Okay, we're going to do some examples in class, and we're also going to do the coffee handout.